Hello everyone. I'm Zhengmao Liu from UPFL and in Switzerland. And today it's my great pleasure to introduce our speaker, Dr. Andrea Pickel from the University of Rochester. So Dr. Pickel is currently an assistant professor in mechanical engineering, and her research focuses on luminescence thermometry, as you can tell from the title. So I guess the purpose is to measure temperatures at extremely small scales, which is very useful and important for these applications, also detailed for device, energy, and catalysis. So Dr. Pickel completed her PhD at the University of California, Berkeley, and have received several awards, including the NSF CAREER Award and a recent recognition as the Scialog Fellow. Today, I guess she will share with us how her team is pushing the limits of temperature measurement, and I really look forward to that. The floor is yours.
All right. Well, thank you so much, Jingmao, for the nice introduction. And thanks again to the organizers for putting together this event and inviting me to be here today and share some of the work that we've been doing over the last few years in my group at the University of Rochester. So as Jingmao just very nicely summarized, one major focus in my group is pushing the boundaries of what's possible with luminescence thermometry, particularly in terms of overcoming conventional limits on spatial resolution and expanding the operating environments where we can perform these measurements. But before getting into the details of how we do that, I'll first introduce some of the technological challenges that motivate our work, which span a wide range of applications, including device thermal management, energy storage and conversion, and catalysis. All right, so when I teach undergraduate heat transfer, I always like to emphasize how there are many direct ties between heat transfer and major societal issues that we face today. And while many of these challenges seem macroscopic at first glance, they're in fact directly connected to many of the types of micro and nanoscale heat transfer problems that my group studies, which I'll get to in just a few moments. As we're all aware, there's incredible excitement about the potential of AI to impact nearly every facet of our lives. But simultaneously, there's increasing recognition that the growth of AI will be accompanied by a huge surge in energy demand due to the enormous power consumption of AI chips. And with this power consumption comes serious heat dissipation challenges, leading to the enormous heat sinks that you can often observe on AI hardware. The growth of AI and other trends like cloud computing are also driving a big increase in the number of data centers. And if you look at the breakdown of energy use for these data centers, a huge fraction, typically 40 to 50%, goes towards cooling. These data centers often draw enormous amounts of water for cooling, and so this massive cooling need has intersected with another major societal challenge of our time, which is increasing water scarcity, particularly in drought-prone areas like the Western US. The trend towards electrification means that lithium-ion batteries are increasingly important for energy storage, but lithium-ion batteries are also prone to catastrophic failure modes like thermal runaway, and so this has led to a growing number of very serious fires. Lighting accounts for about 6% of electricity use in residential buildings and 17% in commercial buildings in the US. So consequently, there's been a big push to switch from incandescent light bulbs to LEDs, which intensified when new energy efficiency standards finally went into effect about a year ago. And these rules essentially ban incandescent bulbs because they use thermal radiation to generate visible light, which is a really inefficient process. One final example that we might not hear about as frequently in our everyday lives, but whose importance immediately becomes clear if you start looking into major drivers of global energy consumption and carbon emissions, is industrial catalysis. And one major example there is the Haber-Bosch process used to produce ammonia for agricultural fertilizers, since the Haber-Bosch process alone accounts for between 1% to 2% of total global energy use and CO2 emissions. So as I mentioned, the examples I just highlighted initially appear macroscopic, but there are actually many direct ties to micro and nanoscale heat transfer challenges, either because the problems fundamentally originate at much smaller length scales, or because we've adapted newer technologies that have nanoscale features. So while LEDs are more energy efficient than incandescent light bulbs, they're still subject to overheating. And in contrast with the macroscopic heat transfer challenges of incandescent lighting, LEDs and related optoelectronic devices like high-power laser diodes experience reliability issues due to overheating in the active regions of these devices, which can contain many thin layers that are sometimes only a few nanometers thick. The electronics thermal management and data center cooling challenges that I mentioned are one result of the long trend of packing more processing power into smaller footprints, with transistors now having nanoscale dimensions. And then newer technologies like wide bandgap electronics operate at even higher powers and voltages, which can lead to localized temperature spikes near their electrical junctions that limit their performance and longevity. Another growing electronics trend is 3D heterogeneous integration, where multiple chips or components with different functionalities are stacked vertically to achieve improved performance and smaller form factors. However, these architectures also introduce new thermal management challenges. For example, internal layers within the 3D stack can lose direct access to external heat rejection elements, and you can also have components with very different temperature limits that are quite close to one another. Thermal transport in lithium-ion batteries is a complicated multi-scale problem involving many thin layers and interfaces, and understanding their thermal properties is important for preventing failure modes like thermal runaway. And so while it's well known in all these cases that these challenges are thermal in nature, our ability to identify the precise causes and guide improved thermal design is limited by the lack of compatible nanothermometry techniques. There are also examples where, rather than being parasitic, localized heating can be beneficial if it's carefully controlled. Emerging dual function materials that both capture and convert CO2 to value-added products can use the heat generated by exothermic CO2 methanation to drive endothermic CO2 desorption, but doing so effectively requires detailed knowledge of the temperature gradients that can develop. Photocatalysis is another growing area that includes both photothermal catalysis, where the idea is to use the conversion of light to heat to drive chemical reactions, as well as plasmonic photocatalysis, where the goal is to exploit non-thermal mechanisms, but heating is often a side effect. And so there's a real need to separate very localized heating from other non-thermal contributions. A common theme that I want to emphasize among these examples, besides the fact that they have micro and nanoscale features, is that these small length scales are often coupled with very challenging operating conditions, including large electric fields, ongoing chemical reactions, and intense plasmonic environments. And so that means that if we want to measure temperature in these systems under realistic operating conditions, then we need thermometry techniques that are broadly compatible with different sample form factors, materials, and operating environments, that have micro to nanoscale spatial resolution, and that are as minimally invasive as possible. If we think about existing thermometry techniques, optical non-contact methods might come to mind as a non-invasive approach. So thermal radiation, both infrared and visible, provides a convenient method to map temperature with well-understood temperature-dependent physics. And there are also many laser-based techniques, including thermoreflectance techniques, which have transformed our understanding of many important thermal transport problems. But as powerful as these optical techniques are, their spatial resolution is fundamentally limited to several hundred nanometers at best by optical diffraction. And for some of the applications I just discussed, that's sufficient, but for others, we need even higher spatial resolution, which leads us to ask the question, can we somehow use far-field optics to circumvent the diffraction limit and measure temperature at the nanoscale? One way to do that is to take advantage of the temperature-dependent luminescence emitted by a single nanoparticle. This approach only allows for measurements at a single spatial point, and that's an important limitation that I'll come back to. But for situations where we need to know the temperature at a single critical location, then this approach works very well. The idea is that we take a single nanoparticle and we place it at the exact location on a sample where we want to measure temperature. We then excite the nanoparticle with a laser and measure the temperature-dependent luminescence it emits. And because the nanoparticle is very small, this minimizes issues of parasitic heat sinking and thermal contact resistance so that the nanoparticle can accurately report the true sample temperature. Even though we're still exciting the nanoparticle with a diffraction-limited laser beam, the key is that the temperature-dependent luminescence and therefore the thermal information come only from the nanoparticle, whose size is much smaller. And so as long as we're only exciting one nanoparticle at a time, then the spatial resolution of the temperature measurement is governed by the nanoparticle size. Next, I want to introduce one of the major classes of nanoparticles that my group works with and that are the basis of all the work I'll show today, which are called upconverting nanoparticles, or UCNPs. There are many different types, but they typically consist of a fluoride or an oxide host matrix that's doped with a combination of lanthanide ions. The most common UCNP composition is a sodium yttrium fluoride host doped with a terbium and erbium ions. They're called upconverting because the sensitizer ions, in this case the ytterbium, absorb two lower energy near infrared photons and transfer this energy to a single erbium ion, which then emits a higher energy photon in the visible wavelength range. And these UCNPs have a number of advantages that make them popular for a variety of imaging and sensing applications. One advantage is that they're extremely photostable, meaning that they don't photobleach or lose their emission intensity over time. They also don't photoblink, which is a sudden temporary loss of intensity. They're also very biocompatible, in part because many UCNPs are excited in the first or second biological windows, which are wavelength regions where tissue is relatively transparent. And for that reason, the bioimaging community has led a lot of their development. UCNPs are also highly tunable, so just by swapping out one dopant for another or changing the dopant concentrations, you can get a big change in parameters like emission wavelength. And my group is also particularly interested in UCNPs because they have excellent thermal, chemical, and high pressure stability. So they can operate at temperatures over 1,000 Kelvin, for example, or under elevated pressures generated by a diamond anvil cell. But the main reason that we're interested in these UCNPs is that they have some particular temperature-dependent emission features that are appealing for thermometry. So as I said a moment ago, the upconversion process begins when the ytterbium absorbs two near-infrared photons and transfers this energy to an erbium ion. Next, the erbium decays non-radiatively to a lower energy excited state before returning to the ground state by emitting a green photon. This is clearly a complicated system with many different energy levels and transitions, but we can really understand the essential temperature-dependent physics by looking at a simple three-level diagram for erbium. What's shown here is erbium's ground state along with two closely spaced excited states from which the erbium can return to the ground state by emitting a green photon. And the key is that the relative population of these excited states is governed by Boltzmann statistics, which is fundamentally where our temperature-dependent signal comes from. The relative population of these excited states is directly related to the relative emission intensities from the two corresponding transitions. And we can see that by looking at spectra taken at different temperatures. So if we divide the emission wavelength range into two bands, lambda1 to lambda2 and lambda2 to lambda3, we see that when we increase the temperature, the emission intensity in the first wavelength band, which corresponds to the transition from the higher energy excited state to the ground state, increases relative to the intensity in the second band, which corresponds to the transition from the lower energy excited state to the ground state. We can then define a temperature-dependent ratio as the integrated emission intensity in the first wavelength band divided by the integrated intensity in the second band. And this approach is known as ratiometric thermometry. And while it's been used fairly commonly for ensembles or large groups of these nanoparticles, back when I started working with them during my PhD, there had been very few single particle measurements and certainly none using particles 50 nanometers or smaller. So a large part of my PhD was demonstrating the first ratiometric thermometry measurements using individual UCNPs, 50 nanometers and smaller. And this plot shows the luminescence intensity ratio as a function of temperature for 5 individual UCNPs. The temperature sensitivity of the technique is quite good, and there's also excellent particle-to-particle uniformity, as you can see from the nearly overlapping calibration curves for these 5 different particles. So one question that naturally arises with single nanoparticle thermometry is how we're going to place a single particle at the exact location where we want to measure temperature, which of course is vital for practical applications. So when I started my own group at the University of Rochester, that was one of the first capabilities that I wanted to develop. And my group is now able to manipulate individual nanoparticles by pushing them with an atomic force microscope or AFM tip. Working with my collaborator, Nick Vamavakis, we've also explored controlling the position of individual nanoparticles by optically levitating them in gas or vacuum environments, which let us do some interesting studies of heat transfer in rarefied gases. And while I won't have time to discuss these projects further today, I'll just note that both these examples actually used a different luminescent probe my group also works with, which are nitrogen vacancy centers in nanodiamonds. So now if we combine temperature-dependent single nanoparticle luminescence and AFM nanomanipulation or optical levitation, we have a very nice way to do far-field optical single-point nanothermometry. And while this is certainly a useful capability, we can also understand that in many situations, we really need a temperature map and not just a single point measurement. And so that led me to ask, is there any way that we can again use far-field optics to circumvent the diffraction limit, but now somehow continuously map temperature at the nanoscale? In trying to answer this question, one place where I found a lot of inspiration is in the world of biological imaging, where to a large extent, this is really a solved problem. Not the problem of using far-field optics for nanoscale temperature mapping, of course, but the problem of using far-field optics to image biological structures with nanoscale spatial resolution. What you see here on the left are several images of biological structures that were obtained using conventional optical microscopy techniques. And now what you see on the right are images of the exact same structures, but these images were recorded using super resolution techniques, which is an umbrella term for several different approaches that can circumvent the diffraction limit. And it's immediately clear that these super resolution techniques are extremely powerful, revealing structure that simply can't be seen with conventional imaging. So how do these super resolution techniques work? Like I said, super resolution is an umbrella term, and so I'll specifically introduce a technique called stimulated emission depletion, or STED, since that's the super resolution imaging method that my group has adapted for nanothermometry. STED is based on luminescent materials, which could be nanoparticles, but here there's no limit on how close together those particles can be spaced. And like conventional imaging, you begin by using a laser to excite emitters from the ground state to an excited state. But what happens next is that you come in with a second donut-shaped laser beam called the stimulated emission depletion, or STED beam. And the STED beam stimulates emitters within the donut to return to the ground state by emitting a photon. That means only emitters in the central zero intensity region can luminesce, and so that drastically restricts the effective point spread function, typically to tens of nanometers and sometimes even smaller. Super resolution imaging has been very impactful in biology, and for that reason, the 2014 Nobel Prize in chemistry was jointly awarded to STED and another class of super resolution techniques. So hopefully I've convinced you that there's a lot to be excited about here, which brings us to the question of why these super resolution methods had never been applied to thermometry. And I would say there are really two major reasons. The first major reason is that traditionally these super resolution methods have relied on organic dyes and fluorescent proteins that lack reliable temperature-dependent emission signatures and are also often restricted to a limited operating temperature range. The other major reason is that historically these techniques have required very high laser intensities to turn off the fluorescence. So I'll now transition into my group's work on developing the first super resolution nanothermometry technique, starting with some of the more recent advances that paved the way for our work in this area. As I mentioned, STED has traditionally relied on organic dyes and fluorescent proteins, but in 2017, two different groups both reported the first demonstrations of STED imaging using upconverting nanoparticles, UCNPs, which again is the same class of nanoparticles that we've used for ratiometric thermometry. Specifically, both these groups showed that sodium yttrium fluoride UCNPs doped with ytterbium and a much higher concentration of thulium than had been used before enable STED imaging with resolution down to about 28 nanometers. So this work was really exciting to me for a couple of reasons. First, UCNP-based STED uses depletion intensities 2 orders of magnitude lower than other probes. And second, ytterbium and thulium co-doped UCNPs had separately been used for ratiometric thermometry in a conventional diffraction-limited mode. So taken together, these advances suggested that there was an opportunity to adapt STED imaging for nanothermometry. But at the same time, there were several major unknowns in terms of constructing the instrumentation, doing spectroscopy rather than imaging, maintaining the STED performance at elevated temperatures, determining whether these heavily doped UCNPs showed any measurable temperature dependence, depositing continuous layers of UCNPs that accurately report the underlying sample temperature and allow for reasonable scan times, and demonstrating that STED could truly detect temperature gradients that diffraction-limited thermometry could not. And while there are certainly additional challenges beyond those listed here, these were some of the most critical points that we identified at the outset. And going forward, I'll describe how we ultimately succeeded in addressing each of these points. Our first step was to construct a custom STED system, and I'll highlight a few particular features. We combine a 976 nanometer excitation laser and an 808 nanometer depletion laser, and these are both continuous wave laser beams. We use half and quarter wave plates to circularly polarize the depletion beam, and we send it through a vortex phase plate to generate the donut shape. We focus both beams onto our samples, which sit on a piezo-controlled nanopositioning stage and a thermal stage. We collect the emitted luminescence, which is primarily in the blue wavelength range, filter out any residual excitation or depletion light, and then we send that luminescence either to an avalanche photodiode or a spectrometer. We use a dry air objective lens that has a numerical aperture of 0.7, and it also has a working distance of 10 millimeters. And so that means we can probe our samples from very far away while simultaneously getting quite high spatial resolution, as I'll show in a moment. This is an image of the system we constructed in my lab at Rochester, and then images of the spatially overlapped excitation and depletion beams. To test the imaging performance of our STED microscope, we used individual UCNPs that were approximately 134 nanometers in diameter. This first luminescence image is what we get if we apply only our excitation beam to image a single UCNP. So this is a conventional diffraction-limited image, and therefore, as expected, we get an emission spot with a diameter of several hundred nanometers. But now, if we apply both our excitation and depletion beams, we get a clear improvement. In this case, getting a full width at half max of about 136 nanometers. And I'll emphasize that these images are a convolution of our true imaging point spread function with the UCNP. So because we're able to image right down to the UCNP size, That suggests that our true spatial resolution is almost certainly better than 136 nanometers. And so again, that means that what we've shown is the ability to do dry air single-use CNP STED imaging with our objective 10 millimeters away from the sample, while simultaneously resolving orders of magnitude smaller than that working distance. We can also look at larger scans containing both single-use CNPs and small aggregates. And if we compare the same scans without and then with the STED laser, we see that the spots appear smaller. And we can also see spots that were previously blurred together start to separate into more distinct isolated spots. So we were happy to demonstrate single UCNP STED imaging, but again, if we want to do ratiometric STED nanothermometry, then we need to do spectroscopy. So first we recorded single UCNP spectra at different temperatures with the goal of identifying temperature-dependent features, and we did indeed observe some temperature dependence. Next, we tested our ability to deplete all the peaks we observed. This is a room temperature single UCNP spectrum taken using only our excitation laser. And if we keep applying that same excitation power, and now we also apply our depletion laser as a Gaussian beam, we see that we can deplete the entire spectrum quite successfully. At higher temperatures, we maintain the same depletion performance. And across all temperatures, we can deplete both our temperature-dependent peak and the longer wavelength peak near 515 nanometers very well. And even though the temperature dependence comes from one peak, we're still interested in a ratiometric approach, since that has advantages over working with absolute intensities. And so going forward, we'll focus on these two peaks. From the spectroscopy results I just showed, we now know that we need to test our ability to maintain similar imaging resolution for two of the lower intensity peaks. So we repeated our single UCNP STED imaging, first using the temperature-dependent peak. We maintain a similar level of resolution at room temperature, and likewise at 350 and 400 Kelvin. We then repeat these experiments for the second peak we're interested in, and the results are again essentially identical. In this case, we can use a simple deconvolution to estimate the true imaging resolution, and we find that it's below 120 nanometers for both spectral bands at all temperatures. From the temperature-dependent spectra I showed earlier, we know that we have a temperature-dependent feature, but we haven't yet rigorously explored whether this approach can enable ratiometric thermometry. And our heavily doped UCNPs have very different emission spectra from conventional lightly thulium-doped UCNPs, and so there was no guarantee we would get a reliable ratiometric thermometry signal. When we plot the ratio of the two peaks shown here for our heavily doped UCNPs, we do indeed observe clear and repeatable temperature dependence with good particle-to-particle uniformity that can be calibrated and employed for thermometry. These measurements were performed using only our excitation laser, and we'd expect to get similar results if we also apply our donut-shaped depletion beam. To verify that, we did the very challenging experiment of temperature-dependent single UCNP STED spectroscopy. And adding in those results, we confirm that, as expected, they fall in line perfectly with our other data. So far, all the results I've shown are for isolated single UCNPs, but to do temperature mapping, we need to continuously coat the sample surface with a layer of UCNPs. So to form UCNP monolayers or multilayers, we use an interfacial self-assembly method. We first drop cast UCNPs dispersed in cyclohexane on the surface of ethylene glycol, and then cover the container to slow down the cyclohexane evaporation. And this results in the formation of UCNP monolayers that can then be removed from the solution. And as you can see from the SEM images shown here, using this approach, we've been quite successful at depositing continuous monolayers over regions many microns wide. STED inherently requires raster scanning, which can be very slow for spectroscopy, since acquiring a single spectrum can take minutes. Even to scan a 1 micron squared region could take hours. And so we wondered if we could instead bring down the scan time by using bandpass filters corresponding to different spectroscopic peaks and using an avalanche photodiode, or APD, to record temperature-dependent ratio maps. We were indeed able to do that, and shown here are ratio maps obtained using APD scans at different uniform temperatures. Because the entire sample is at the same temperature, we expect to record the same ratio at every pixel, and indeed the maps are pretty uniform. And we can also easily tell these different temperatures apart from one another. As a final validation step, we perform similar APD scans at uniform temperatures in both diffraction-limited and STED modes, in this case on a UCNP multilayer, primarily consisting of double-layer regions, just to boost our signal to noise. We can then overlay the mean ratio and standard deviation from the APD scans at each temperature in both modes on our prior spectroscopic data, and we again get an excellent match. So finally, we wanted to show that we could really use this technique to resolve temperature heterogeneities that can't be seen with diffraction-limited measurements. To do that, we need test structures that can generate steep temperature gradients. So we fabricated microscale serpentine heater lines made of nichrome on quartz substrates. When you send an electrical current through these heater lines, the current density concentrates at the inner corners due to a geometric effect that's called current crowding. And so the resulting joule heating also concentrates at the inner corners, and you get temperature gradients where the inner corners of the heater line are at higher temperatures than the outer corner. Well, we found it was very challenging to get self-assembled UCNP monolayers to land exactly where we needed them. We had more success drop casting UCNPs onto the heater lines. And here we got a cluster of UCNPs that spans the diagonal from the inner corner to the outer corner for one bend of the serpentine. So let's first look at the control case of zero applied current. What I'm plotting here is the temperature rise at 3 locations relative to the temperature at the outer corner. And as expected, with no applied current, the data points are essentially flat, meaning that we don't detect a temperature gradient for both diffraction-limited and STED measurements. And I also want to mention that one challenge we're still working to address is that the STED laser can heat optically absorbing low thermal conductivity materials like nichrome. So there's also a laser heating contribution that's being subtracted off here. Next, we apply a DC current to the heater line. And starting with the diffraction-limited measurements, we indeed observe a temperature rise as expected. However, the data points are again essentially flat, meaning that we can't detect a temperature gradient. But now, if we add in our donut-shaped beam and perform STED measurements at the exact same points, we do indeed resolve a temperature gradient with a higher temperature measured at the inner corner than at the outer corner, exactly as we expect. And this measured temperature gradient also agrees reasonably well with the prediction from our finite element simulation. So there's, of course, more work remaining in terms of developing STED nanothermometry into a practical nanoscale temperature mapping technique, but we're excited about the successes that we've had so far, including this demonstration that STED can resolve a temperature gradient that can't be observed with diffraction-limited measurements. All right, so I'll now switch gears and spend the remainder of my time here sharing 2 shorter stories where we've applied UCNP thermometry to address some important challenges related to energy and sustainability-oriented applications. And here we'll return to diffraction-limited measurements with spatial resolution in the range of about 500 nanometers to a micron, and focus on bringing UCNP thermometry into some challenging operating environments, specifically in the presence of ongoing chemical or electrochemical reactions. So many experimental demonstrations have shown that chemical reactions can be strongly enhanced when the reactions are performed on the surfaces of illuminated plasmonic nanostructures, which is known as plasmonic photocatalysis. And specifically, it's frequently been observed that you can enhance the reaction rates or selectivity relative to traditional thermal catalysis processes that involve bulk heating of large reactors. And so this has led to a number of compelling potential applications. First, plasmonic photocatalysis has now been demonstrated for many common industrial reactions, such as ammonia production, which, as I mentioned early on, accounts for about 1 to 2% of global energy use and CO2 emissions. So being able to perform this reaction more efficiently would have a huge impact. There's also been a lot of interest in using plasmonic photocatalysis to harness sunlight in order to generate sustainable fuels like hydrogen. And I'll note that plasmonic photocatalysis is appealing in terms of harnessing solar energy to drive many different types of reactions, not just sustainable fuel production. And this is possible because, unlike earlier semiconductor photocatalysts, plasmonic photocatalysis can operate under fairly low intensity, visible or near infrared illumination. And finally, there's evidence that plasmonic photocatalysis can be used to drive reactions that are energetically unfavorable and therefore challenging to perform with conventional methods. So these applications are all exciting in terms of their potential to reduce energy consumption and enable more sustainable chemical production. But there's also been a lot of uncertainty about the fundamental mechanisms behind plasmonic photocatalysis, which are important to understand in order to optimize and ultimately scale up this technology. And in particular, there's been an enormous amount of debate about the relative contributions of non-thermal hot electrons versus surface heating to the observed reaction enhancement. And so one way that people have tried to disentangle these effects is to not only use the Raman signals from the reacting molecules to monitor the chemical reaction, but also use anti-Stokes to Stokes Raman peak intensity ratios to measure temperature. And using this approach, different groups have studied the same chemical reactions, yet come to very different conclusions about the importance of heating for plasmonic photocatalysis. One potential reason for these discrepancies is that while Raman peak intensity ratios do depend on temperature, there are also other non-thermal factors that can change these ratios, particularly while a reaction is occurring. So our approach is that we still use Raman spectra to monitor the chemical reaction, but to measure temperature, we instead use the temperature-dependent luminescence emitted by UCNPs. We can use a single 808 nanometer laser to both photocatalyze the chemical reaction and excite our UCNP thermometers, which is made possible by using terbium and erbium-doped UCNPs with an additional neodymium dopant. Because the UCNP emission is shifted all the way into the visible range, while the Raman signal remains much closer to the excitation wavelength, these two signals naturally separate in the spectral domain, which I'll show in just a moment. And we use the photocatalyzed dimerization of 4-nitrothiophenol, or 4-NTP, to dimer-captoazobenzene, or DMAB, as a model reaction. So when we excite our samples with the 808 nanometer laser, we see, first of all, as I mentioned just a moment ago, that the UCNP and the 4-NTP Raman spectra naturally separate in the spectral domain. We also find that the same range of laser excitation intensities can progressively photocatalyze the 4-NTP dimerization and excite our UCNP thermometers. So as we increase the laser intensity, we see new Raman peaks associated with the DMAB product appear. And we also see that a peak associated with the 4-NTP reactant decreases, both of which indicate that the reaction is occurring. And while it's difficult to see by eye in this format, the green UCNP spectra are also undergoing a change in relative emission intensity as we increase the laser power that indicates a temperature rise, which we can observe more clearly if we plot the same UCNP spectra on a normalized basis. To quantify the reaction progress, we use the intensity ratio of a Raman peak associated with the product versus a peak associated with the reactant. So we see that the Raman ratio initially increases as the reaction progresses and then saturates towards a constant value. Meanwhile, the temperature is roughly constant during the measurement period, which is expected since we estimate the initial transient heating to be many orders of magnitude faster than our integration time. So this is representative data for one excitation intensity. We repeat these measurements for several different excitation intensities, and we observe a clear correlation of the reaction with the surface temperature. But because that temperature rise is also correlated with absorbed laser power, a non-thermal effect could also show the same type of correlation. So next, we turn the laser intensity way down to a level where it can't catalyze the reaction and only briefly exposed our samples to the laser to record Raman spectra. We then used our thermal stage to increase the sample temperature to the highest laser-induced temperature rise we measured, but the reaction never occurs. And so we conclude that heating alone can't catalyze the reaction. So these results seemingly indicate that the photocatalysis is non-thermal, but we performed one more experiment that suggests things are a bit more complicated. So if we again apply the lowest laser intensity that can catalyze the reaction, photocatalyze the reaction, and now we increase our sample temperature first to 320 and then to 340 Kelvin using our thermal stage, we actually do enhance the reaction. And so we conclude that although heating alone can't catalyze the reaction, heating does enhance the photocatalysis process. So there's clearly a complicated interplay between temperature and plasmonic effects here. But we're encouraged that this approach of simultaneous operando UCNP thermometry and Raman spectroscopy can be applied towards the goal of disentangling these effects. And so we're now working on experiments as a next step where we can keep the laser intensity constant but alter the temperature rise, which we can achieve by designing samples that have nearly identical optical properties but different thermal properties. All right, so finally, in my last few minutes here, I'll share a second example of taking UCNP thermometry into challenging operating environments. And I'll share some recent work we've done on internal temperature measurements of operating lithium-based batteries. And this work was done in collaboration with my colleague Wyatt Teneff, who's an expert in lithium batteries. So as lithium-ion batteries become increasingly important for applications like renewable energy storage, there's been a growing emphasis on understanding various degradation and failure modes in order to improve battery safety and reliability. In particular, there have been some interesting recent investigations into the thermal properties of battery layers and temperature gradients within batteries and their connections to battery performance. So one study showed that thermal contact resistances between different layers could account for up to 65% of the total internal battery resistance. These contact resistances can also increase during formation cycling, leading to an increase in the total battery thermal resistance of more than 70%. Another very interesting recent paper showed that simply the presence of mild temperature gradients, even in the absence of any applied current and at moderate absolute temperatures, could induce lithium leaching. And so these types of studies motivated us to develop a method to monitor internal battery temperatures during operation. And certainly there have been prior measurements of internal battery temperatures, but there are shortcomings associated with the various thermometry methods that have been used, such as using macroscopic sensors that can interfere with the battery operation, only being able to probe certain components within the battery, or experiencing challenges with separating temperature changes from other effects. So we wanted to develop a method that could work without interfering with the battery operation, could be applied to all layers within the battery, and could isolate the influence of temperature. So what we did is we disassembled both commercial primary lithium coin cells and lithium ion coin cells, and we deposited UCNPs onto the various layers. Here they're shown on the cathode, but as I'll show in a moment, we put them on other layers as well. We make a small hole in the cell case and in some of the battery layers when necessary to provide optical access to the component we're measuring. We then seal the aperture with a Kapton film, and we're able to successfully record temperature-dependent UCNP spectra with this setup. Next, we wanted to ensure that the addition of the UCNPs wouldn't have a negative impact on the battery performance, so we conducted several tests using lithium-ion half cells. First, we performed galvanostatic cycling and found that the capacity retentions for cells with and without UCNPs were extremely similar, indicating that the addition of UCNPs has a negligible impact on the cycling performance. We also used electrochemical impedance spectroscopy to assess the impact of the UCNPs on the interfacial kinetics, and the results again indicate that the UCNPs don't have a detrimental impact. Before performing operando internal temperature measurements, we calibrated the ratiometric thermometry signal for UCNPs on different battery components to account for any potential differences in the local optical environment that could affect the temperature-dependent ratio. From there, we moved on to operando thermometry. So for discharge currents up to about 15 milliamps, we found that across 3 different coin cells with UCNPs deposited on the cathode, separator, and anode, the internal temperature measured by the UCNPs and the external temperature measured by a thermocouple attached to the outside of the cell case are in agreement. And so in addition to validating the fidelity of the UCNP thermometry, these results confirm that there's no detectable laser heating. Next, we wanted to test what happens if we apply currents beyond 15 milliamps. And we found that when we increased the discharge current to 20 milliamps, we measured a temperature difference of just over 2 degrees between the cathode and the battery exterior. The measurements I've shown are all for batteries with glass fiber separators so far, but we also tested commercial polyolefin separators, which are very commonly used in lithium-ion batteries. For one of the coin cells with that type of separator, we were able to apply an even higher discharge current of 65 milliamps. And in that case, we measured a temperature difference of nearly 8 degrees between the separator and the battery exterior. And if you work on batteries, you'll likely recognize that these aren't necessarily realistic operating parameters. The discharge currents are very high, and joule heating will dominate under these high currents. But we're excited that we've demonstrated the ability of UCNPs to measure internal temperatures in operating batteries. So going forward, we're planning to apply the same approach to larger format cells like pouch, prism, or cylindrical cells that operate at higher currents and should experience larger internal temperature gradients. All right, so to summarize, my group's research focuses on pushing the boundaries of luminescence thermometry, particularly in terms of spatial resolution and operating environment. And ongoing projects in my group include the work on STED super resolution nanothermometry, operando thermometry and reaction monitoring during plasmonic photocatalysis, and operando internal battery thermometry that I discussed today. I'd also like to acknowledge the various funding sources that have supported my group's work, including support for the STED nanothermometry work from an NSF CAREER Award, and initial support for the plasmonic photocatalysis work from the ACS PRF, and current support from NSF. Finally, I'd like to acknowledge the Ph.D. students in my group, who of course were instrumental to all the projects that I discussed today. I'd particularly like to acknowledge Xiang Yi, who led the majority of the work that I shared today, along with Ben Harrington and Dinesh Bhamidi. And with that, thank you again for your attention. I'd be happy to answer any questions.
Thank you, Andrea, for the amazing talk. And now the floor is open for questions. I guess feel free either to unmute yourself or raise your hand, so I'll call on you.
I have a question. So the slide where you have the blue plot, I think it's the last, that's one of the one before. So there's like an echo.
Sorry, which plot? I think I missed the last part.
The last slide.
That one, or?
Yeah, the bottom right. So that so there's like a weird echo on my end. The temperature difference that you record, did you actually do like a thermal resistance network to try and like see if that agrees with what you would expect?
Yeah, it's a great question. So we did do maybe not a simple thermal resistance network, but we did like a COMSOL finite element model to account for kind of the full geometry. And so the short answer is that, yes, we can kind of simulate these types of few degree temperature differences. I'd say maybe the caveat is that there's a lot of kind of unknowns about the internal battery properties, like what are the thermal conductivities or thermal interface resistances, how do they change with cycling? So, we use kind of the best numbers that we can there based on other results in the literature. But I think it's hard to know that we're really, correct there for the actual batteries we're testing.
Thank you.
Mm-hmm.
I think we cannot hear you very well, at least on my end.
No. How about now?
Yeah, great.
Okay, good. So excellent talk. I did have a question. I think you have that result again on your summary slide about your measurements when you're using the confocal laser and the stead laser. So this result right in front of us, you show the red data points with the error bars for the confocal laser. I would have expected that these error bars would be really large in that you have not really a systematic error coming from the confocal laser. It's just not able to map that out. Whereas when you do the correction, you do get good results. So my question is, I guess, what accounts for those error bars and why are they not accurately, or even if the error bars are large, not representing the temperature differences?
Yeah, so in terms of kind of the major sources of the error and the uncertainty, so I'd say there's two dominant things. So one is that we did what we call like a batch calibration, where we, developed a kind of average ratio versus temperature calibration on a bunch of other single nanoparticles, so not the ones that we're applying here. And we kind of account for, the variation in those different calibration curves that we're then applying to this kind of uncalibrated particles in this situation. So that's, one source of error. And if we had done the calibration on this particular sample, which we just didn't for practical reasons, but, you could in general, that could help reduce some of the error. The other major source is that we did 12 repeated measurements at each of these kind of 3 locations. And so there's some trial to trial variation just associated with like the stability of especially the depletion laser and like mechanical drifts in our system. So those are the dominant sources of error. And so, certainly I think there are paths to improving them and we'd like to work on that. Fundamentally, I think our temperature sensitivity is pretty good here, but definitely, dealing with all those kind of practical issues will help us reduce those error bars.
So there is just a quick follow-up. You're saying it's just what you're showing is just a random error. It seems like there is some sort of systematic error that's coming when you use just a confocal laser, and you're saying that's not the case. If you did many more calibration measurements, you think you will capture the temperature difference a little better?
Yes, I'm not sure if I might be missing your question, but basically, the way I'd see it is that in this plot, for the confocal measurements, so the red data points, I mean, they're flat because we don't detect the temperature gradient, and that's just because the spatial resolution isn't high enough, so we spatially average it out. So that's kind of expected, although it's a shortcoming of
I got
that.
it.
And then the reason the green ones can catch it is because the resolution's higher. So I'd argue that that part's a good thing. With the confocal, we'll never be able to capture that steep gradient. Yeah.
Okay, great, thank you.
Zheng Mao, can I ask a question?
Yes, Matthew, I sir unmuted. Yes.
So, Andrea, first of all, this was a beautiful talk. I really congratulate you for your work. I have a couple of questions which are not much science related, but are more technology related. You briefly mentioned this. I want to try to understand whether the temporal limitation of the technique. And the reason why I'm asking this is that in many phase change phenomena, which is my domain of interest, we are interested many times at micro scale or even smaller time scales. So I want to get a sense of whether you think there's an opportunity with this technique to go down to those temporal resolution. And that's the first question. The second question, very quickly, is whether you had the chance to test this technique in a humid environment or essentially in the presence of liquid.
Sure, yeah. So just the first question you're asking about, like temporal, like time resolution?
Yeah.
Okay, yeah, so that's a great question. And I would say it kind of depends on the specific implementation. So for the super resolution, kind of STED stuff, where we're really pushing the spatial resolution below the diffraction limit, it's pretty tough because our signals are just so small. They're very weak. And so we have to acquire, for a pretty long time just to get enough signal. And so maybe there's some clever games you could play there, but I think it's hard to go, super fast just because of that. But if we go back to the diffraction limited measurements, where again you can still get down to 500 nanometers or so it's not bad. There we get much stronger signals, and so we can push, to go much faster there. I think for the battery measurements, we were typically only acquiring every second, but the fundamental limit with the UCNPs is their lifetimes, which are fairly long in the world of fluorescent probes. They're typically hundreds of microseconds to milliseconds. So, but that's like your fundamental limit. So I think that might at least be fast enough for some of the applications you're interested in. And then to your second question about, kind of humid environments or in liquid. So while we have personally not done that, I think that's absolutely possible. Just going back to, like I said, most people who work with UCNPs use them for biological applications. And so they're always doing their measurements and, kind of water, other, fluids is very common. So you can use immersion objectives, and that's quite doable, I think.
Beautiful. Thank you. Thank you very
Sure.
much.
Yeah.
Any other question? I guess we can have one more. Roman, we are not hearing you. But
Are you able to hear me now?
Oh, yeah, now we can.
Okay, sorry. Matteo actually asked my question, and I just wanted to say again, fantastic talk.
Thank you.